Nice photo.
Oh,
Hello. Can everybody see my desktop now?
Yes.
Okay. Okay. I think we're ready to go. So today we're going to do some more stuff with parsing. And maybe today will be the last day that we talk about parsing. And then we'll go back to functions. Okay. But I want to, if you, I say there's a link here that says see that you have homework assignment 5. It's actually not up there yet. Okay. I started working on it last night. I haven't finished it yet. So, but I want to start by describing to you what the homework assignment is. So I can describe it to you. I can tell you the idea of it now, and hopefully it'll be ready by tomorrow, and then you can start working on it. But so let me explain the idea of it first, and then you're going to write a parser. Okay. So let's see. Okay. Now here's the idea. If we go back to language 7, okay, language 7 doesn't have really a parser. It's got this thing build tree, which just reads the tree language. Our language is a tree language. Okay. So everything in our language is a tree language. So this is a tree with root, if, and 3 branches. Okay. And while is a tree with root, while, and 2 branches. Okay. Our parser, for example, the parser we're using, which we call build tree, is kind of dumb. So for example, it doesn't know that if should have 3 branches. If you write if and give it 5 branches, our parser wouldn't know the difference. Okay, so it has no way of knowing that an if root should have only 3 branches. Our parser has no idea that a while root should only have 2 branches, and that a begin loop would have begin loop could have an arbitrary number of branches, but it has to have at least 1. Okay, it has to have at least 1. You can't have a begin that's just a leaf. That wouldn't make sense. All right. So one thing you're going to do is you're going to write a real parser for this language. So the real parser would see that a while is followed by 2 expressions, and an if is followed by 3 expressions. Okay, so we'll see how you can write that. We'll talk a little bit more about parsers today, but that'll solve one of our problems, because in our interpreter, see, the interpreter is this evaluate function. Our interpreter does a lot of work that interpreters should never have to do. So for example, in evaluate if, it does this. See, there's where it checks that an if statement is supposed to have 3 branches. An if statement is supposed to have 3 branches. Well, our parser doesn't know that. So our evaluator says, oh, if there's not 3 branches on an if, do a runtime check and throw an exception. Well, you should never be checking for things like that at runtime. Okay, that's why we should have a proper parser. Okay, so what we're going to do is we're going to take your homework assignment is to remove a lot of these runtime checks from the evaluator and have the parser do as many of them as possible. Okay, so you're going to write a parser for this language, and it'll eliminate a lot of the runtime checks, but not all of the runtime checks. Okay, it's like here's an example that here's something a parser can't do. Okay, we have a rule that says that you can't set a variable until after it's been declared. Okay, now, oops. If you do something, suppose you're writing your program, so you're writing a program. Okay, this is okay. You can say var x6 set x5 or 7. Okay, that's legitimate, right? Because the variable is declared before it was set. Okay, Now reverse the order of these. Syntactically, there's nothing in the grammar that says that sets have to come after vars. There's no way the grammar can have a rule saying set must come before var. This is something that you just can't do. That's something you just cannot do in a grammar. Grammars are called, the kind of grammars we're writing, these grammars actually have a name. They're called context-free grammars. Okay, that means that any one of these things here, that's the right rule for set, and there's no context to it. Yeah, it is. See, we actually have a context. You're not supposed to use set until after you've used var. So this set is in the wrong context. This set should be after the var. But our grammars are technically called context-free grammars. They can't tell the difference between var before set and var after set. Our grammars cannot tell the difference between that and that because they're technically context-free grammars. So even when you write a parser, even if you wrote a really good parser, your parser can't tell the difference between this and this. But you could have what we're going to do is we're going to have a stage in our language, something called static analysis. We're going to create a static analysis stage. Right now, here's how we tokenize. So somebody gives us a string. We tokenize it. Then we parse it. Okay. Then we parse it to an abstract syntax tree. Okay. And then we evaluate it. That's how we've been writing things. We have the tokenizer. Yeah, the tokenizer takes the string and tokenizes it. So we have a token, this tokenizer, so we tokenize the string, parse it to an abstract syntax tree, then evaluate the abstract syntax tree. Okay, we're going to put a step in between here called static analysis. It's also sometimes called semantic analysis. Some people call it the static analysis step. Some people call it the semantic analysis step. This step can detect these problems. It can detect things that are context-sensitive things that our grammar can't pick up. So your homework assignment is going to be to write a better parser and then to write a static analysis thing. Okay, now here's how you can imagine static analysis working. Okay, static analysis is like a baby evaluator. Okay, it doesn't evaluate the program entirely, but it evaluates the program a little bit. So for example, this program now so far has a parse tree that looks like this. So it's a prog. And under the prog is two steps. Okay. Under the prog, there's a var and a set. Okay. And the var does x6 and set does x. Okay. So here's what an evaluator, the actual evaluator, when it hits prog, it creates the global environment. Then it puts var in the global environment with x and 6. Okay, so it creates the global environment and it puts x x6 into the global environment, okay? So over here, we can imagine the global environment table. Okay, so x6 is in the global environment, okay? Right? Now, so that the evaluator the prog would create the global environment, var would put x6 into the global environment, then set will update it, okay? Now, the static analyzer will do essentially almost the same thing. The static analyzer will create the global environment. When it sees var x, it'll put x into the global environment. And then when it gets to set, it'll just check. It won't actually do the set. And if a static analyzer isn't an interpreter, so actually all it would need to do is say, is there an x in the global environment? Because if there is, set's okay. Okay, so the static analyzer does part of the work of evaluator. It'll need to put things into the environment, but like here, it won't update the environment. A good example of the difference between a static analyzer, here's a real good example of the difference between a static analyzer and a global. Suppose I write while less than x 100, 1,000, 1 million. Whoops. Okay, there's a little bit of code. Okay. All right. Now, is this a valid program? Okay, so now this parse tree would have I don't know if I can get all this parse tree. Okay, so there's a less than here, and the less than compares x okay, and okay, so this is what the parse tree would look like roughly. Okay, so the static analyzer would hit the prog, create the global environment. It would say, oh, there, I have to put x into the global environment. Then when I get to here, the static analyzer would just say, is there an x? Because you can't set x unless there is an x. So it just look in the global, it wouldn't even really look at the 7. It would just say, is there an x in the global environment? Yes, there is, so fine. Now, the static analyzer, when it gets to the while loop, is not going to execute the while loop. It's just going to analyze the while loop. It's going to say, oh, let's see, there's a x variable here. What should I do? Check that there is an x in the environment. Don't really look at it. Just say, is there an x in the environment? Yes, fine. Similarly, the print statement will have, you're going to print the x. The static analyzer, when it gets to print, will just say, well, what are we printing? It'll see x, and it'll say, well, there better be an x in the global environment. Check that there's an x in the global environment. Fine. So the static analyzer will visit this node of the tree, visit this node of the tree, visit this node of the tree, visit this node, this node, this node, and visit this node and this node. But it would only visit these things once. Like, it won't do the while loop. It'll just check the while loop. Okay. On the other hand, if your program looks like this, well, for example, suppose your program looks like this. Okay. Now the static analyzer, this branch here is gone. This branch is gone, for example. The static analyzer will see a set, and it'll say, oh, I should look in the global environment. And I'll find an empty global environment, and then you get a static analysis error. At that point, the static analyzer would just halt and say, on line 6, static analysis error, undefined variable x. Okay? So that's what they're saying. So that's what a static analyzer would do. It would look for things that are undefined. Andrew?
Would it really be best to have to go through the process of constructing the environment table? Wouldn't it be better to just be able to quickly identify what scope you're in and do a quick text search to see if that variable's been defined yet?
No, it's actually probably way easier. Let me put it this way. If you do it this way, you can reuse about 80% of your evaluator code.
Oh,
Because essentially what you're going to do is you're going to take your evaluator, throw out parts of it, and just keep certain parts.
hmm.
So it's actually probably easier to write the static analyzer as a evaluator that doesn't do the for loops, and it does as little evaluating as possible. So
Mhm.
think of it as the static analysis does as little evaluating as necessary, but it should build all the global and local environments. It will have to build the global, because for example, you have to worry about there being a local variable. So for example, here's the kind of things you have to worry about. Okay, what should the static analyzer find out there?
X has been initialized,
Right.
therefore it's
So
okay to use it elsewhere.
no, no. What's it going to find out? What's the static analyzer going to realize here?
I mean, you have initialized X twice, but is that illegal in our language?
Yeah, it is.
Oh, well, then it should throw an error.
Yeah. So it's just like in Java. You're not allowed to declare a variable 2 times. Okay. But on the other hand, if you do this, now what?
Still a syntax error. You have a open set of parentheses in there.
Oh, okay. Let me just close it. Yeah.
Okay,
See now
then
the
that's
idea.
okay.
Yeah. See now that there is hiding that there. So this X now hides that X. So how would
Hmm.
you know that? You have to build the environments carefully. The static analyzer has to build the environments. So the static analyzer would build the global environment and put X in it. Then when it sees to begin, it would build a local environment. It would build a local environment that would be, and then it would put an X in the local environment. Okay. And then when it gets down to here, so then when it gets down to here, it looks up X and it says, well, yeah, there's an X in the local environment. Okay. Right. So you still need these now, for example, and then for example, now, is that okay or not?
Yeah. Oh, well,
Well,
yes.
yeah,
Yes, it is.
yeah, because that now, even though you have a local variable, you create a local environment, you're still setting the X in the global environment.
Hmm.
Okay. So the static analyzer does need to build all the environments so it can check things like this.
Hmm.
What it mostly doesn't need to do is it doesn't need to do any of the looping, and it doesn't actually need to make function calls. Let's look a little bit about function calls in a minute. Yeah. Okay, so the static analysis will now the static analysis is trying to check things that can't be determined by the grammar, but still can be determined statically before you run the program. So they can be determined by looking at the code. That you can tell that you can check the error by just looking at the code, but not by parsing the code. Here's a real good example of something that the static analyzer can figure out. Okay, uh, we can fun. We'll see. What was our syntax for functions? I forgot all of a sudden. Oh, so we say fun f lambda, oops. Okay, there's the definition of the squaring function. F takes a number and squares it. So fun variable lambda expression. Did I do that right? Yeah. Fun, name of the function, then a lambda expression. Okay, right. Now, here's how I call a function. We call a function with the apply keyword. So we say apply expression, expressions, okay? Apply F2, 1, 2, 3, okay? There's no way a grammar can tell that there's anything wrong there. Think about it. Is this grammatically incorrect?
I want to say yes, it is.
But only in context, right? Because see, now suppose I do the following. So remember, our grammar for fun is that I can have as many variables as I want there. Okay, so let me do this. Okay, is this grammatically correct?
Yeah.
Is it grammatically correct now?
No.
See, you can't say that. It's either, grammatically correct has to do with this grammar. How can this guy suddenly change from grammatically correct to being grammatically incorrect when I didn't change the grammar and I didn't change him? See, I'm not changing him. I'm not changing the grammar. So how can you say he's suddenly shifting from correct to incorrect? See, what it is he's correct in the context of this application is correct or incorrect in the context of this definition. But our languages are context free. So we have to basically say that this is correct and this is correct. We cannot have a grammar enforce a rule that a function has to be called with the same number of parameters it was defined with. This is a famous example of what we mean by context-free grammars. Even though it's a rule in Java and C++ and all these other languages, that if you have a function with two variables, if the function is defined,
you should pass it two variables.
Right, but that's not enforced by the grammar.
Is there a way to make it enforced by the grammar? Have like some way of it knowing that?
I've read that it is, but it makes the grammars amazingly complicated.
I see.
Yeah, I've read that it is possible. I've never seen it done, but I've read that yes, you can make the grammars, but I have a feeling that the answer is really no. So, but it's easy to analyze a program and find out that this is a problem, okay? Because here's what we're going to do. We have remember, we have two pieces of a parse tree here. There's the part here that has the fun. So the fun part looks like this. Fun has it's going to be F, and then it's going to have okay, here's the parse tree for the fun. Here's the parse tree for that. And then over here, somewhere else is going to be the parse tree for apply. Okay, so the parse tree for apply. Okay. Okay. So what's the static analyzer going to do now? In one part of the program is this thing. So this has been parsed, and you have in the global environment, you'll have F pointing to this lambda. So in the global environment, so over here, I can put the global environment. And in the global environment will be F pointing at a lambda. So it'll be pointing at a lambda. So we really know it's pointing down here at that lambda. Okay. All right. So now that's correct. There's nothing wrong with that. Now the static analyzer gets to this line of code. The static analyzer doesn't need to call the function. All it needs to do is do a comparison of the number of branches here with the number of branches here, and they should agree. So the static analyzer can say, oh, you've got an apply of F. The apply has 3 parameters, F had 2 parameters, static error, static analysis error. The analyzer doesn't need to do the calling. It doesn't need to create the local environment that, remember when you apply a function, you have to create a local environment that binds the parameters to that binds the actual parameters to the formal parameters. In static analysis, you don't have to actually do all that work. All you have to do is count. The static analyzer looks up the function, looks up the lambda, goes over to here, counts how many branches the lambda has, that's how many parameters. Then it looks at the apply, looks at here, counts how many branches this have, they should agree. And that's all it can check. Okay. So the static analyzer can check function calls. The parser can't check function calls, but the static analyzer can. Okay. So your homework assignment is going to be essentially well, first you'll write the better parser. You'll write the parser of this guy that actually says things like if has 3 branches. Okay. And then you'll write the better parser, and then you'll write the static analyzer. It'll mostly do 2 things. It'll check for undeclared variables and redeclared variables, like we showed up here. It'll check for undeclared and redeclared variables, and it'll check that function calls match up, that the arguments to a function call are the same number as the parameters of the function call. Okay, and then that will eliminate a lot of code in the evaluator. So for example, like let's go look for evaluate apply. Oh, I think I passed it.
There it is.
Here's evaluate apply. Essentially what you're going to, okay, now, well, see, okay, see that runtime check? You're going to move it from the evaluator to the syntax analyzer, the semantic analyzer. In fact, a lot of what you need in your semantic analyzer is already in the evaluator. You'll just have to rearrange some of the code. Okay, so here's the actual the 2 lines of code that check that the number of parameters in the function call is equal to the actual parameters in the number of actual parameters in the function call is equal to the number of formal parameters in the function definition. Okay, so it's just 2 lines of code. But now that'll be pulled out of the evaluator. The evaluator, since the evaluator is going to run after the static analyzer, the evaluator can assume that every function call is correct. Okay, so once this has been moved out of the static analyzer, out of the evaluator into the static analyzer, that means our evaluators faster. You know, in the case of languages like Python, people ask, well, why is Python slow? One of the reasons is because it's got more things that have to be runtime checks than there should be. Okay, the fewer runtime checks you need, the faster your interpreter can be. So if we can move runtime checks out of the evaluator and into the static analyzer, we can speed up the evaluator. Okay. Not every runtime check can be moved to the static analyzer. Okay. Let me give you an example of a runtime check that cannot be moved to the static analyzer. And this hints at something that we're not doing in this class that we should be, but it's kind of hard. Okay. So suppose I have var x5, var y true, var w and xy. Okay, what's wrong with that?
You are trying to apply a Boolean operator to a Boolean and an integer
Yeah,
operand.
so it's a type error. Okay, so we've got a type error. X has type integer and it should have type Boolean. Okay. Now notice that that is a context error. Okay. See, look, the error is here, but it's not a syntax error. It's a context error. So if I go up here and change this to false, now there's no error down here. So it's not a context-free thing. It's a context thing. Okay, so this cannot be detected by the parser. This is another example of something that no parser can detect this. No parser can do type checking. The static analyzer can do type checking. Java and C++, they all do it, but it's difficult. Yeah, if we were doing a longer course, or if we were doing, that's one of the things that we should really do. That would be like one of the next important topics to do, but we don't have time to do all these topics. Add a type checker to our static analyzer. The static analyzer should be able to say, oh, I know the type of this, and I know the type of this. Okay. Now, actually, we almost could do that. See, you put var x, like if you could almost do this. I'll show you what really stops you from doing this. Here's the global environment. Okay. Well, in my global environment, I've got x5. My static analyzer knows that. And my static analyzer knows that I've got y true. So the static analyzer can say, well, what type is x? Well, it's int, and can say there's an error. Okay, right? So our static analyzer could find this error. But let me show you what's much harder. Here's the problem that we really can't do. Now, it isn't so much the type of x and y that's important, it's the return type of f that's important. Okay, so now we have to actually know about the return types of all our functions. To type check this, I would have to analyze f to try to figure out what its return type is. But f doesn't have a return type in our language. Here's a funny function, real simple function. Okay. The function I takes in one parameter and just returns its value. I stands for identity function. What's the return type of I?
Whatever you give it.
Right. So is it returning a Boolean or an int?
Yes. Also
Yes,
no.
right. So up here, you can't. Now, suppose I replace this with I. I'm screwed. I cannot figure out what the type of this stuff is because I will return. Yeah. Now then I can just say, well, I is a special. You get into really complicated situations where I's return type depends on I's parameter type, and you get into very touchy logic problems.
So
Type checkers are very, very much a branch of mathematical logic because you can see here that if I want to know what the type of this thing here is, I have to know what the type of I is. But some I's, the type of the return value depends on the type of the input value. So this can become nightmarish. So we're not going to try to do type checking because if
doesn't
it wasn't for the functions, we could do it. So we could go back to language 5, for example, that didn't have functions and actually do type checking because it only has variables. Okay, so without functions, if I just want to do, if I just this, there, z, and x, y, that I can type check. X has the value of an int and y has the value of a Boolean, so that fails because I know what the value of x is and I know what the value of y is. So even the static analyzer can figure out that this is wrong, but the static analyzer, this is too hard. Because of the return type of the function, we just, and
doesn't Haskell do this exceptionally well?
yeah, and it took a lot of very smart people to figure that out. That's the type inference engine. The guy who figured that out got the equivalent of a Nobel Prize. It was
Oh,
not not a trivial matter to have figured that out. He figured out an algorithm for type checking that worked really, really well. Okay, and it's called um, it's called Hindley-Milner type system. Okay. Okay. It's referred to as the Hindley-Milner type system, and Milner is the guy who got the equivalent of like the Nobel Prize. Okay. I don't know what happened to Hindley if he got a consolation prize or not, but that the invention of the Hindley, that's what Haskell uses. Haskell uses the Hindley-Milner type system. Okay. So
and it
Haskell can,
somehow deals with identity and
pardon me,
variable return type functions.
say again.
And it somehow deals with variable return type functions.
It, I forget how you have to deal with the identity function. Even in Haskell, the identity function is a little bit weird. Um, I think it might actually cause them even a little bit of problem because it's just kind of. I think what happens is in Haskell they pick a fixed type for x. So it either is the identity function on ints, or it's the identity function on doubles, or it's the identity. So it isn't a polymorphic identity function. Okay, so even it doesn't become what you would call a polymorphic identity function. It becomes a identity function of only one type. So this would not type check. This would end up not type checking because this would try to make I return a Boolean and return a Boolean with it given an int, and it won't work. So this will fail, but it won't actually define I this way. It'll have to give X a type. So it'll become the identity function on doubles, or the identity function on integers, or the identity function on strings, or whatever. Okay. All right. So we won't. So our static analysis will mostly consist of variable declarations, and function calls. And we won't do type checking. Type checking is the other famous part of static analysis, but it's too hard. We won't try to do it. So we can handle variable declarations, function calls, but not type checking. Okay, so that's what your homework assignment is going to be. Whoops. Yeah. Okay. All right. Now, that's a rough outline of what the homework assignment will be. You know, you're going to write the static analyzer. Now, let's talk about how to write a parser. Okay. Well, let me save this. Okay. There. Okay. All right. Now, let's what we want to do is we're going to do this folder here that's inside the zip file, this infix arithmetic recursive descent folder. We were doing baby expressions, so now we're going to remember the baby expressions were all x plus x plus x or x times plus x times x. But now we're going to switch from these. But the baby expressions were all trying to build up the idea of addition and multiplication. You know, of two operators, one being more have higher priority than another. Now let's look at a grammar that does true infix arithmetic. So you download this folder on grammars and parsing. Okay, there's a folder in here called folder 6. Now, I haven't had time to write all this up. We're going to do. Uh-oh. Let's see. Old version of the software. What happened to the? Oops. That's the old version. I thought I updated it last night on the web server. Let me check again. Okay, either I forgot to post the newer version on the web server or something goofed up. So I have to get it from elsewhere on my computer. So so the current, what we want to look at is not on the web server yet. I thought I uploaded it last night. Okay, let me. Yeah, okay, there's the current version. So I have to remember after class to update the version on the web server. So there's a folder in here. Okay, now there's infix arithmetic recursive descent and infix arithmetic shift reduce. I meant to actually write two different parsers using two different algorithms, but I haven't had time to finish this other algorithm. This is the one we want. I mean, your homework assignment is to write recursive descent parser. Recursive descent parsers are the easier kind to write. Shift reduce parsers are a little bit harder to write, but I meant to like write both of them to show the difference between them. In this folder, there is a shift reduce parser of postfix arithmetic. So if you're interested, you can look in here. That is a shift reduce parser for postfix arithmetic. And it's based on this thing called the Shunty-Yard algorithm. Okay, so we're not going to go into that now. So okay, so we're not going to go into that, but it's in there if you're curious. What you need for the homework assignment is a recursive descent part, and that's what we've been talking about. In the baby expression folder, all these algorithms were recursive descent parsers. Okay, so let's look at this infix arithmetic recursive descent parser. Let's look at the grammar. We're going to write a real parser for this infix grammar. So now remember in the baby language in the folder on baby languages, we ended up with expression, term, and factor. We had expression, term, and factor because we had three priority levels. We had multiplication had the high, well, the highest level of priority was parentheses. Then below that was multiplication. Then below that was addition. Now we have 1, 2, 3, 4, 5, 6 levels of priorities because this language added a negative negation, a unary negation operator, and it adds an exponential operator. So it adds a unary negation operator at a precedence level that's higher than multiplication, but lower than exponentiation. So addition and subtraction are the lowest priority. Multiplication and division have the next priority. Negation has slightly higher priority. Then exponentiation has next higher priority. Then parentheses have the highest priority. So we end up with 1, 2, 3, 4, 5, 6 layers. Okay, and if you look here, expression is left recursive, so it's left associative. Multiplication, which is the term, is left recursive, so it's also left associative. Now, look at signed. It's the, well, signed isn't binary operator, so we can't make it associative. So signed doesn't have an associative. Now, look at this guy. Factor calls base and signed, then sign calls factor. That makes factor right recursive. See, that makes factor through sign, sign goes to factor. So you have right recursion through sign. So that makes this guy right associative. So these two operators are left associative. This operator ends up being right associative because he doesn't look recursive. Factor calls base and signed or base, but signed calls factor. So that makes factor recursive, and he's recursive on the right, so he's right associative. Okay. Oh, there's also a unary square root operator that has very high priority or precedence. Okay, so actually there's a unary negation operator and also a unary square root operator in this language. Okay, now we don't leave things left recursive. We turn them into iteration. Okay, so the left recursive things are turned into iteration. That's what we saw in all that stuff that was done in the baby language folder. That was this idea of how what you needed to do was take left recursion and turn it into iteration. So this one's turned into iteration, this one's turned into iteration, and then this one, the other one stays recursion, the right associative one. Okay? That's the language that we're writing a parser for. We're going to write a recursive descent parser. So we're going to write functions that get these things. So we're going to write a function called get expression, get term, get signed, get factor, get base, and get number. So we're going to write 1, 2, 3, 4, 5, 6 functions. And we can kind of read off what happens. What does get expression do? The first thing it does is call get a term. Then it looks to see if there's any more tokens. See, this is 0 or more. So get expression calls get term. Then in a while loop, it asks if there's more tokens, match a plus or a minus, then call get term. Then loop, match a plus or a minus, call get term. Then in a loop, so so get expression will call get term, then it'll say while more expression, match this or this, call get term in the while loop. What does get term do? Get term calls get signed right away. Okay. Notice that's why we can't have left recursion. If we had expression call get expression, then get expression would call get expression, which we call get expression, and the left recursion would turn into infinite recursion. That's why you can't have left recursion down here. You have to get rid of it before you can write the recursive descent parser. Okay, but term can call get signed and then go into an infinite loop, go into a while loop. While there's more tokens, match a multiplication or a division, then call get signed. Then loop again, match a multiplication. If there's more tokens, match a multiplication or division, call get signed. If there's more tokens, match, call get signed. Okay. Now,
So
what?
recursive descent parsers only work when there's a guarantee that at every step you will consume something.
Yes. Yeah.
Otherwise, you just recurse down forever.
Yeah. Yeah. And so every one of these, like every one of these things consumes tokens. Okay. And when you're getting an expression, you get a term, you consume those tokens, and then if you get a plus, you consume it, and then you'll call get term on what's left of the tokens. Okay. For example, signed will do something. This one's a little bit tricky. Signed has an optional negation sign in front of factor. So signed will have to do a peek. It'll peek at at the next token. If it's a minus sign, it will build a parse tree that says there's a minus factor. And if the thing it peeks at is not a minus sign, then it just calls get factor. So it peeks, and if it peeks and sees a minus sign, it builds a parse tree of negative factor. And if there isn't a minus sign as the next token, it builds the parse tree for factor. Okay, so sign does a little peek before it calls get factor. Okay, then get factor immediately calls get base. Then when get base returns, it does something similar to signed. It peeks at the next token. Now notice that here, the optional is up arrow signed. So here the optional was just the multiplication operator. Here the optional is the whole thing. So what it does is it peeks to see if there's an up arrow. If there's an up arrow, it builds a parse. It parses the up arrow and gets signed. If there isn't an up arrow by peeking, it's done. So you call get base, and if there's another token and it's an up arrow, get the arrow, then call get signed. Okay. Now what about get base? In a minute we'll look at the code and see that what we're describing in words is what the code does. When you call get base, it needs to decide if it's this case, or this case. See, it's got 3 cases now. None of these others had cases. Okay, this one's got 3 cases. So what you do is you peek. Okay, if you peek and see a left paren, you're in this case. If you peek and see square root, you're in this case. If you're not in that case, by the process of elimination, you must be in that case. Okay, so you peek. If you see a left paren, you call get per expression, and then you consume the left parentheses, call get expression, and then consume the right parentheses. On your hand, if you peek and see square root, then you call get base. And if you peek and didn't see this or this, then you call get number. Okay, let's look at the code. Here's the parser. Now let's look at let's pick one of these and match it to the code over here. So let's just start at the top. Okay, expression, get expression. Okay, get expression is when we return a Boolean. Boolean means it succeeded in parsing the thing. This thing doesn't build a parse tree yet. So right now we're just trying to parse without building a parse tree or an abstract syntax tree. So this is the simple step. First, just write a parser that just returns true when something parsed and false when something didn't parse. Okay, so the first thing you should do is call get term. So it calls get term and asks, the result says that thing parsed or didn't parse. So it calls get term. Okay, now it has to go into this loop. While there are more tokens, and if you peek, you see a plus or minus. So this is the code that says while there is another token and it's a plus or a minus. So while there is a token and you peek and get, see, this is a little trick. I peek and it returns a string. And I ask for the index of that string in plus or minus. And if it's in plus or minus, I'm going to get an index of 0 or 1. If it's not, I get an index of -1. So if it's not in, if the thing I peaked is not plus or minus, I get -1. So it's a tricky little it's a tricky little trick for checking that I got a plus or a minus. I mean, if you want, you could just write this out real verbosely, that peak return to plus or peak return to minus. But this is a little trick for writing it in one little line. Okay, so that's this while loop. Inside the while loop, you just call getTerm. Okay, and then you return the result. Okay, so while there's a token and it's a plus or a minus, while there's a token and it's a plus or minus, call getTerm. Okay, now what does getTerm do? Real similar. It calls getSigned right away. So it just calls getSigned. Okay. Okay. Then it has its own little loop, almost the exact same loop. While there's a token and it's a plus, a times or a division, call getSigned. See, he'll call getSigned. Okay. What does getSigned do? GetSigned has to peek and see if there's a minus sign. Okay. So if there's a token and you peek at it and it's a minus sign, okay, then you consume the operator token, that's the negation operator, and then you call getFactor. Otherwise, if this is not true, you just call getFactor. See, if this is not there, then you just call getFactor directly. Okay, so now when we build a parse tree, we'll see that this one here will put the operator on the left of the parse tree, and it'll put the factor on the right of the parse tree. So when we build actual trees, we'll see that that's going to be the left and right branch of the tree for that operator. Okay, now what about factor? GetFactor should call getBase right away. So here it calls getBase. Okay, and then it needs to check if there's a token that's a up arrow. Notice it's not a while loop, it's just an if statement. It's just going to check one time. Is there a token? Is it an up arrow? If there is, get the operator and get the sign term. GetSigned. Okay, so if there's a token and it's an up arrow, this will become one branch of the tree. Eventually, this will be one branch of the tree, and this will be another branch of the tree. Okay. Here's one that's a little bit harder. GetBase, because remember, GetBase had has to really check for three things. So it's going to have essentially, notice it's got 4 branches here. You expect it to have 1, 2, 3 branches. Instead, it's got 1, 2, 3, 4 branches. And the reason is, the first branch is just checking that we haven't run out of tokens. This is just something, see, there's this throw parse error. If you get, there's always a chance that somebody wrote their program incorrectly. So it's possible that you get into this get base and you've just run out of tokens. You should have at least, you see, you have to peek and see if there's a left parentheses, a square root, or a number. But you can't peek if something's not there. So the first thing it does is check that there's really tokens. If there are no tokens, just halt the process of parsing. Okay, so then the 3 cases here of left parentheses, square root, and number are this else if clause, this else if clause, and this else clause. Okay, all right, so this first clause checks if there's a, okay, we know there's a token because we passed this test. So we know there's a token, so we peek and it's a left parentheses. So if we peek and see a left parentheses, okay, we consume the left parentheses, we'll eventually put it in a tree. We call getExpression. Okay, now we're supposed to get a right parentheses. But we have to write a little bit of boilerplate code here because it's possible that the person forgot to close the right parentheses. So you could have someone who wrote a left parentheses, an expression, and forgot the matching parentheses. So you have to first check that there really is another token. If there isn't another token, blow up. Then you have to check that there is a token that matches right parentheses. And if there's no token, blow up. If there is a token but it doesn't match right parentheses, blow up. Okay, so this is error checking that there really is a right parentheses there. Okay, now if you're not in that case, you could peek and see a square root. If you peek and see a square root, you grab the square root token and you call get base. So you grab the square root token and you call get base. Those will end up being two branches of a tree. Okay, and if you don't have that case and you don't have that case, process elimination is you must be in get number. Okay, all right. Okay, and then get number check. Now see, number is supposed to be a valid Java double. Okay, so number first checks that there's tokens, because you could have gotten to this branch, you could have gotten here and there really weren't any more tokens. Okay, well actually not really, because we already checked that there were tokens here. But to be doubly sure, I checked that there's the tokens here. Okay, just to be doubly sure, since he's going to have to grab some number tokens, first make sure there really are tokens, then grab the token, let Java parse it. Not that we care about the value is, but just let Java parse it. Then that'll tell us if it's not really a double, we'll get a number format exception. So then we'll have a parse exception. But if it does parse, then we're okay. So we'll let Java do the parsing of the actual double. Okay, so there's the whole parser. Okay, there's the parser that doesn't build an abstract syntax tree or a parse tree. Okay, all right. So we can run this. Well, we won't. We don't. Well, we have a program to test this. Okay, here's a bunch of infix expressions. These all parse, and then there's some down here. I purposely wrote some examples that have parsing errors. Like there's no operator here, so there's something missing here. Here it says plus, and then it just runs out of operators. Okay, or operands. Here's an illegal operator. Okay, I forget what's wrong here. Oh, this language doesn't allow variables. This language is a language only of literals, like a calculator. So this baby language doesn't have variables in it. Okay, so now this I can compile. I can run it. Okay, and it reports that parsed, that parsed, that parsed, that parsed. Okay, so it just tells you that it doesn't build any data structures or anything. It just tells you which. Now, see, notice down here, you get this thing didn't parse exception, syntax error, unexpected input 7. See, it didn't know how to, after the 4 should have been an operator. There's really a missing operator, so it got to the 7 and said, I don't know what to do with it. On the other hand, in this one, parse error, unexpected end of input. It got to the plus, should have found another operator, but there was no more tokens, so you get unexpected end of input. Okay, here you get a the error. Now you can get a sense of why you get lousy error messages whenever you work with compilers. There's really a bad operator there, and but because of the way the parser is written, it really expected there to be this thing began a term, 7 is a term, and then there should have been a closing parentheses. Because it doesn't know what @ means, it really said, well, what should have been there is a closing parentheses of a term there. So instead of saying illegal operator, since it doesn't have a clue what an @ really means, it doesn't even know it's supposed to be an operator, it says, oh, you should have a closing parentheses here. Okay, so you can start seeing how you get funny error messages from compilers because they have a hard time figuring out what really should have been there. This
Is
one's a
there
little bit
anybody
easier.
who does error error reporting well?
Yes, Rust.
Really?
Yeah, and I think it's because it's such a new language, they were able to make use of all the theory and all the advances that have been made in compile. Like you take GCC, you can't really go back and fix it because then what would happen?
You would just have to rewrite an ocean of code, an
Right,
actual ocean of code.
you break everyone's build scripts because everyone knows how to parse error messages, and you'd be breaking all kinds of debuggers. You just make a mess if you try to go back and fix GCC.
Well, I mean,
So
forget breaking everyone's code. It's just that's a massive code base.
yeah, uh-huh. Well, no, no, no. Well, yeah, I'm saying so GCC is big. You're right. You're right. Fixing GCC would be rewriting a massive amount of GCC. Yeah, that's a good point. So it's a double problem. On the one hand, you'd have to rewrite a massive amount of GCC, but you'd also be breaking everyone's build scripts if you started changing the error messages.
Yeah,
Yeah. On the other hand, Rust was a very recent language. Rust has actually people praise it for the quality of its error messages. It has really interesting error messages that tell you exactly what you did wrong. So people have made real advances in compiler theory in the last 20 years or so, and Rust was able to take advantage of all those advances. So it
hmm
actually has really good error messages.
they didn't end up like JavaScript where you could replace someone's semicolon with a Greek comma and watch them spend the next 2 hours of their life
No,
losing their own mind.
no, the Rust language, almost nothing's as bizarrely irregular as JavaScript. So the Rust language is very regular. That helps make the error messages better also. Okay, now let's look at another. There's three versions of this parser. Okay, why are there three versions of the parser? Okay, we want to be able to, we're used to working with abstract syntax trees. So here's a parser for the same grammar that builds the abstract syntax tree. Now that's what our other parser was building. The crummy parser that we've been using built abstract syntax trees. So now we have a parser that's a good parser that also builds abstract syntax trees. So for example, here's the test program for it. Is that right? Oh, um, yeah, we know what the abstract syntax trees would look like. So this abstract syntax tree should just be square root 25. The root node is square root, and it's got one node below it. The abstract syntax tree for this, because multiplication has higher precedence, that'll be at the root, and on its left will be the sum of 2 and 3. So we should be able to get the abstract syntax trees out of this. Okay, now the different, let's compare the two parsers. On the right is the parser that only checks things, doesn't actually build an abstract syntax tree. On the left is the parser that builds an abstract syntax tree. So look at how get expression changes a little bit. So instead of returning a Boolean, it's going to return a tree now. Okay. When you call get term to start off, you call get term and you get a tree. Okay. Now that tree is going to then become part of the overall parse tree, but we have to check for the plus and minuses that add on to it. Okay, so this term now is going to be the left branch of the tree, and then as we do plus and minuses, we'll add them on to the tree. Okay, so notice that if I have a plus minus term, okay, I call get term. See, they're calling get term is just like calling get term there. But here, get term becomes the right branch of a tree that has the operator at the root, the previous result on the left branch, and the get term is on the right branch. So this builds the abstract syntax tree with the operator, whichever it was, plus or minus, at the root. What was on the left of the operator is on the left side of the tree. And then what's on the right side of the operator, this is the, remember, we're supposed to be left associative, okay? Left associative means, let's see, oh, wait a minute, yeah. Oh, yeah, yeah, this is doing left associative because as you iterate through this, it's really tricky. Every time I do this, I have to remind myself why this is doing left associative. Okay, because it's taking this, okay, this tree is this tree here. Okay, so when you've built this tree up, you take the previous tree and put it on the left of the new tree. So you always take the previous tree and make it the left branch of the new tree. So you're accumulating on the left, which is what's making it left associative. The pluses that are on the left keep shoving down lower and lower and lower in the parse tree. So for example, this very first one here, he ends up on the left of this guy. He ends up on the left of this guy. But then when you iterate again, you take him and put him on the left. So this original one is on the left of the left. So he's being pushed down in the parse tree. Okay, it's very tricky. Yeah, but if you draw enough pictures as you think through the code, you draw pictures of the data structures as you read the code. And you have to actually draw. You have to iterate through this loop. You have to do it yourself. It's something that everyone should do at least once. Draw these trees. Take a string like you imagine like 1 plus 2 plus 3 plus 4. Okay, and then you parse that using this algorithm. Okay, and you just see what's going to happen. What's going to happen is you're going to get a parse tree that has a 1 and a 2. You'll get that parse tree. That's the parsing of this part. Then when you get to parse this guy, you'll take that parse tree and put him on the left and build up from him with a plus three. Now what you have to do is you have to convince yourself that that loop this loop here, that this call created that tree. Then the first iteration of the loop gets to this plus here. Oh, I'm sorry, actually, this one actually created the tree that's just the 1. Okay, so this get term created 1. The first time through this loop took 1 and put him on the left of plus 2. That was the first time through this loop. So now the first time through this loop result is this tree here. There. Then the second time through the loop for the second plus, it'll take this tree, put it down below that plus there, and put 3 on the right. That was the second time through this loop. The third time through this loop, this is now result. The third time through this loop, it's going to push result on the left, and it's going to create another. See, it's going to put result on the left, the operator at the top, and now it's going to put the 4 over here. It'll build the tree bottom up. The first tree was 1. The first time through the loop built this tree here. Second time through the loop built this tree here. Then third time through the loop, finished the tree off. So the tree was built from the bottom up. Really tricky. Okay, that's the star doing left associative. And now you can see it's left associative. 1 plus 2 got done first, then plus 3 was added on, then plus 4 was added on. Okay, do this yourself at home. Make sure you can take an expression like this and walk your way through this code with a piece of paper and see how it builds that data structure. Okay? All right. Now, okay, so this parser goes through and builds abstract syntax trees. Okay? And if you, there's a test program that tests this parser. Let's look at it real quickly. Let me see. What time do we finish? I keep losing track of time. Oh, we ran over, right?
Mm-hmm.
Yeah. So we'll stop here. So what we're going to do is we still need to talk about the what's called. Let me just show you one thing real quick. This is kind of neat to see. The difference between a parse tree and an abstract syntax tree. So this is something you can read about over the week.
Yeah, you had some postings about that on your website.
Yeah. See, there's a parse tree. There's an abstract syntax tree. There's the parse
There's
tree.
the parse tree. They're a lot more verbose.
Right. See, it's still the square root of 25. See, the square root of 25. Notice how it's the square root of 25. Now, here's an even more complicated one. There's the abstract syntax tree. It's 2 plus the multiplication of 3 and 4. There's the parse tree. The parse tree records everything you went through as you went through the parser productions. Notice it's 2 plus 3 times 4. In a parse tree, the leaves are the tokens. In an abstract syntax tree, notice the abstract syntax tree shows the order of operations. The parse tree shows you the syntax of it. Parse trees get really complicated really fast. Even for very simple expressions, the parse trees can grow immensely big. Like there's a simple expression, there's the parse tree. Like here, there's just 3 nodes, there's the parse tree. And they just get more and more complicated. Like here's a real simple tree, there's its parse tree.
Would it even be sensible to look at the parse tree of something like Java code?
Yes,
Oh.
because you have to, well, the compiler doesn't. The compiler does not care about the parse tree. So the parse tree is important really to the IDE. It's got to keep track of all these parentheses.
I was more referring to like a human reader. Like, would you ever want to?
Would you ever want an abstract syntax tree?
Yeah, I can imagine that.
Yeah, because it does tell you the order of operations and things like that. No,
If you're dealing with some exceptionally tricky code.
yeah, the abstract syntax tree captures the meaning of the expression. No,
Mm-hmm.
the only people who care about parse trees tend to be IDEs.
Okay.
They need to keep track of all the parentheses and things like that. And English professors, I mean, when you parse natural languages, you want the parse. There are no such thing as abstract syntax trees for English. This is where natural language diverges from computer languages. Parse trees are what English language, human languages look at parse trees. Computer programs actually look at abstract syntax trees. So we both do parsing, but linguists parse to syntax trees, computer scientists parse to abstract syntax trees. But IDEs use syntax trees. Okay, so there's a bunch, you can look at these examples. They're kind of interesting to look at. Compare the abstract syntax trees to the parse trees. And that's where we'll pick up on Monday. We'll talk about the difference between parse trees and abstract syntax trees. Okay, so as always before, if you have any questions, send me an email. Oh, I'm trying to get the videos up somewhere. I couldn't get them up on YouTube. YouTube seems to be messed up now. So maybe Blackboard can hold them. They're kind of big.
I can set a posting if you need to. I have a big 8.5, like 8 terabyte drive sitting around.
Yeah, but then this is a lot of I/O. Yeah, you probably do not want to be hosting 1 gig, 2 gigabyte, multi-gigabyte videos.
My download's great. My upload isn't all that great. I
Yeah,
remember that now.
I'm gonna see if I can get them up on either YouTube or Blackboard. I'll
Hmm.
put a link to them as soon as I have them available. But I'm trying to make them available. So I think it's a real good idea that the videos should be available. Okay.
I do have a suggestion for you.
Mm-hmm.
Um, so when you're drawing the diagrams, you might want to pick up something like this.
I have one.
Yeah, it will
I
be a
have
lot.
one.
Yeah.
It still makes it hard. Yeah, I've been using it. It still doesn't help a whole lot. I have one.
Hmm.
Yeah, I have exactly the same thing you have. I have a Wacom tablet.
It should be a lot easier than typing that stuff in.
Well, yeah, but then I have to switch to a whole different window. See, they don't
Hmm.
let me do the draw. One thing that Zoom doesn't let me do is share the desktop at the same time I share
Annotate it.
the whiteboard. See, I have to switch from desktop to whiteboard.
I swear there's an option to annotate.
I'd like to have the whiteboard and the desktop together. Like you don't see my desktop now, do you?
No,
Yeah,
I
see,
thought there was an annotation option.
I haven't figured it out yet. What I want to do is have the whiteboard and the desktop side, to have the whiteboard as just something on the desktop. So maybe I should switch to a different whiteboard application instead of using Zoom's built-in one. Maybe I
View
can find a
options.
better,
Annotate.
or just
Um,
use Paint. I probably should just use Paint.
Yeah, that's what I was gonna say.
I
Wait,
hadn't even
it
thought about,
looks like it does have an option to do this, or at least for viewers.
let me see. Okay, I
So
here's my desktop with Paint on it. So there's you see Paint, right?
yeah,
Did somebody draw on that? Yeah, who's annotate? Who's doing that? That's kind of neat. Who's
me.
doing that? You.
I
So,
am using my pen.
wow, you're annotating my desktop?
Oh, that's coming up on your desktop.
Yeah,
Wait,
get
what?
off my desktop.
Why is it
Do you
letting
see?
me do that?
I have no idea. You're like scribbling on my desktop. It's in a way it's kind of cool, but I mean, talk about, you could do a denial of service. You could just start erasing my whole desktop. You're actually right. I don't know what you're writing on actually. That's pretty
So
weird.
for
What tool
me,
did you use? Hmm.
if I go to like, I don't have my Zoom application maximized. I have
Hmm.
at the top a view options button, and then I went to annotate and then draw. So I'll need to change my Wacom settings so that it focuses
Oh,
on
annotate. Okay.
one window instead of, or one
Okay.
display instead of my entire
That's
array.
me. So everyone sees that, right? I'm
Yeah.
annotating the desktop also now. Okay, yeah, we can all scribble. Huh, that's interesting. Okay, so that's annotate, but it's actually scribbling on the desktop. I wonder how do you, let's see. Now I can erase. I wonder, can I erase you and me? Oh yeah, I can erase whatever. So I can erase what I wrote and I can erase what other people wrote.
All right, so this should let me focus on just one display instead of all three of mine. So my scaling should be better.
Okay, that's it. So there might be some interesting way to, yeah, I have to think about, uh-huh. So, so now we're all drawing together on the desktop. Yeah, kind of neat. Yeah,
Yeah.
I don't, yeah, is it easier to draw trees this way? Yeah, now here I'm using my pen to draw. It's a lot easier than drawing with a mouse.
God, yes, I've seen some professors doing that, and the results
Yeah,
are not great.
I've had this tablet for years. I don't use it all that often anymore, but I've had it for years. So I'm not that good at it, but yeah, it's a lot easier to draw with a tablet, yeah, than with a mouse.
Hmm.
Okay. Oh, but that's kind of neat. So, but the, then you could go here and you could erase. There's probably a clear, is there? Oh, clear all drawings, clear my drawing, clear all drawings. Okay. And then this one, then there's also my paint. This is, no, this is me annotating still. This can get confusing. So how do you get out of annotation?
I'm guessing the red X button.
Red X? Okay. Right.
Yeah.
Yeah. So that got out of annotate. Yeah. So now, then this is me drawing on my paint program. But I left the annotate. You know what I got out of the annotation? The annotation stayed on the screen. It didn't disappear. I thought it would disappear with the annotation app. That's interesting. The annotation stayed there. Okay. That's kind of weird. I hope it doesn't stay there forever. I'm sure it'll probably disappear when we exit Zoom. Okay, well that's good. Well, thanks for the tips. That's going to be useful. The annotation might be real nice. Okay, I'm going to go ahead and end the class. So if you have questions, send me emails. Look for another programming assignment up there. Hopefully, I will be up there tomorrow where you write the parser and the semantic analyzer, and I'm going to try to get the videos up there. Okay. Let's see, stop sharing. And then I go, okay, I'm going to end the meeting now. Goodbye.
Goodbye.
Bye.